Section 4.7, which are antiderivatives. Antiderivatives you can consider as opposite of derivatives, right? Kind of. What does it mean, antiderivative? We are going to say a function capital F, we show it in capital F here, is an antiderivative of f on an interval I if, there's a typo here by the way, it should be capital F by the way, right? Okay, I made a correction about this should be f prime x is equal to f of x. Capital F is going to be an antiderivative of little f if derivative of the capital F of x is equal to f of x, okay? So be careful about that. And if you consider a function, if the antiderivative exists, it's not a unique one. You have tons of antiderivative, and the most general one is f of x plus c, because if you take the derivative of a constant, you get a 0, right? So if capital F is an antiderivative of f on an interval I, then the most general antiderivative of little f on I is capital F plus c. C is a constant, so this is given as a theorem because the derivative of c is 0, right? These are called the family of antiderivatives of the function, okay? 3x squared, so little f is 3x squared, antiderivative is x cubed plus c, and see this is a family of such curves. As you change c, they don't overlap, as you would see, right? It's a good picture to see what's happening. So what are the antiderivative formulas for some functions that we know of? For example, if the function is x to the n, as long as n is not negative 1, the antiderivative is x to the n plus 1 over n plus 1 plus c. Let's take the derivative of this to check whether we get this back. Take the derivative of x to the n plus 1, take the power to the front, and decrease the power by 1. So we get x to the n here, n plus 1s are going to cancel, so we get x to the n back, okay? So antiderivative of sine kx is negative cosine kx over k plus c. This is the general one, most general antiderivative. Let's check it out. Take the derivative of this cosine. The derivative of cosine is negative sine. So there's a negative here too. They cancel. We have sine kx, but the derivative of the inside function is k. K's are going to cancel. So we get sine kx. And the derivative of c is the 0. Okay? So for cosine kx, we have 1 over k sine kx plus c. For secant squared kx is 10 kx over k plus c. Cosecant squared kx, we have cotangent kx over k, negative in the front, plus c. This is, since we know the derivative of secant is secant tangent, so antiderivative of secant kx tangent kx is 1 over k, secant kx plus c. And the derivative of secant kx is secant kx minus secant kx cotangent kx, so the antiderivative of this is negative 1 over k cosecant kx plus c. So these are nice formulas that we should be aware of. And we have a constant multiple rule and sum over difference rule. If we have a function k times f of x, k is a constant. Antiderivative is easy. It's just you keep the k. The antiderivative of little f is capital F and put the c here. Okay, that's all to it. If you have the product, a sum or difference of the two, the antiderivative, general antiderivative is going to be just sum or difference of the two of the antiderivatives, capital F and capital G and plus C. Okay, these are the nice rules that we should be aware of. Let me open up the book. Okay, so we have a question about, this part is antiderivatives and motion. We see an example about the antiderivatives in an example. Example 5 in our book, a hot air balloon ascending at the rate of 3.6 meters per second is at a height 24.5 meters above the ground when a package is dropped. Okay, and hot air balloon that's going up, and the speed is 3.6 meters per second, and and it reaches 24.5 meters above the ground, and a package is dropped. How long does it take the package to reach the ground? That's the question. And I'm going to go through the solution together with you, okay? Let's see. Okay, you can see the picture down here. Look. See, the velocity V0 is the initial speed going up, 3.6. And then we have this dv dt, which is gravity, negative 9.8 towards... okay. We were analyzing the picture. They drop a package. S of t is the distance at time t. Alright, but this is the distance from the ground of the package. Okay, this S of t. So how are we gonna deal with this problem? Let's go back to the question. Solution. So we are gonna say V of t as the velocity of the package at time t, and S of t denotes its height above the ground, and the acceleration of gravity, it is known, 9.8 meter per second squared, meter per second, meter per s squared, I'm sorry. And of course we are assuming that no other forces are affecting the situation. Then what is the acceleration? Acceleration dv dt. dv dt is equal to negative 9.8, and we have this equation, and then we have the initial condition. This is a differential equation. Actually, in Math 202 class, you're going to see them a lot. And we have this differential equation, dv dt is equal to negative 9.8, and the initial condition, which means it's the initial speed or velocity, 3.6, going upwards. So going upwards is our positive direction. Opposite direction, which is going back downwards, is negative. That's why actually acceleration is negative here, okay? And velocity is going up 3.6 up, so it's positive. All right. The first thing we are going to do, we are going to solve this differential equation. But how do we do that? So we are going to ask ourselves, what is the what's the antiderivative of such a function? The antiderivative is of what's the antiderivative of dv dt? Okay, which is v. It is negative 9.8 t plus c, because if you take the derivative of v with respect to t, you get negative 9.8 plus 0, right? So we look at the antiderivative. And we solve this, but there's the c unknowns. We use the initial condition at 0. This is 0. C is 3.6. So we found the velocity function of this problem. V of t is equal to negative 9.8 t plus 3.6. Okay, that's how it is here. All right, but what they're asking is, let's go back to the question. Okay, let me see. Let me look at the book actually. It says, how long does it take the package to reach the ground? That's the question. So they are interested in the time. How long does it take? Okay. So let's find what the S of t is. S of t is the distance from the ground. So when it hits the ground, S of t is going to be 0, right? Then maybe from there we will be able to find the time. Okay, so our goal is to find S of t. We just found V of t. It is not enough yet. V is the same as ds dt. We know that, right? ds dt is equal to v, which is equal to negative 9.8 t plus 3.6. And then this is our new differential equation. And then there's an initial condition as well. S of 0, which is at time t is equal to 0, the package was 24.5 meters above. So this we can easily write. So in order to solve this system, we ask ourselves what is the antiderivative of this function, which is s. So for which function, if I take the derivative is going to be equal to this. Okay, then s could be negative 9.8 t squared over 2. So we are going to get negative 4.9 t squared, and then plus 3.6 t plus a constant. Let's take the derivative of this to see whether we get that. ds dt is equal to 2 times 4.9, which is 9.8. There's negative, keep the negative, plus, times t, plus the derivative of this is 3.6, and the derivative of a constant is 0. So this is s of t, this is the distance from the ground. And we have s of 0 as well. Let's put it in to find our new c. This is a different c than the previous c, of course. S of 0 is going to be s of 0, 24.5. Put 0 in, 0, 0 plus c is equal to 24.5. So we got c is equal to 24.5. So we just found s of t is equal to this equation. That's fine. Next, we want to use s of t equals to 0. This is when it hits the ground. The distance from the ground is equal to 0. So we equate this to 0 and solve for t, which is this equation. And we can easily do that quadratic formula. And t is equal to negative 3.6 minus plus square root of delta. Delta is b squared minus 4ac. 3.6 squared minus 4 times a times c. You get this number over 2 times a. 2 times this, negative 4.9, is negative 9.8. This is the quadratic formula. And from here, we use our calculator to find t is negative 1.90, t is equal to 2.63, but t can never be negative, so the package hits the ground, okay, after 2.63 seconds, okay? Hits the ground. So we found the answer as it is. Next, we continue with the definition. Now, after we learned about the antiderivative, here's a new definition, which we called indefinite integral of the function f with respect to x. So consider the collection of all antiderivatives of f, and we want to represent it in a nicer way, and this is where we use the integral sign. Integral of f of x dx is going to be equal to the collection of all antiderivatives of f, okay? Here, this is of course the integral sign, okay? F of x is called the integrand, look, integrand, and of the integral, and x is the variable of the integration, okay? So integral sign, integrand, and x is the variable of the integration, okay? So we are going to use this in our next lecture.